Yeah, thank you for the introduction. I'm very pleased to speak in front of you. My talk is about viscosity-depending ion transport in high-energy lithium-sulfur batteries. Let me shortly tell you something about the German Aerospace Center, or how we call it, the DLR. It is the Aeronautic and Space Research Center of the Federal Republic of Germany. And it has not only this aeronautics and space research topic, also transport, security, and energy. Sorry, is it loud enough? Yeah. So, and we have, the DLR has about 8,000 employees in 20 locations all over Germany, also with international focuses and research corporations. And I here had the Stuttgart facility and also our department, our institute, and I'm from the Department of Electrochemical Energy Storage, and this is our latest battery lab. Now we're getting new facilities, we're a growing department. So, yeah, sulfur, is it really a promising active material? I think so, but there are remaining challenges, like we already heard yesterday and also today, about the insulating nature of sulfur and also the solubility of the intermediates. And accordingly, adding a huge amount of lightweight carbon has been proposed to go against the insulating nature of sulfur, but this is sacrificing the volumetric energy density at all, which is not so compatible at all, and also the gravimetric energy density if we talk about additions of about 40 weight%. And furthermore, we heard about the losses of capacity through the solubilities and what all can more happen about this. And I'm going to show you some of my results. I'm more from the field of cathode layer producing. And this is, sorry, there's another sheet. Yeah, I just want to shortly talk about that. You all know this. There's only half as much voltage like in comparable lithium-ion batteries, so therefore we need for this requirement, especially, for example, for transportation, we need a higher aerial capacity, almost a double aerial capacity, and even so we have a huge specific capacity that is obtainable from sulfur. We need at least a fifth around the active material loading, which can be obtained with lithium-ion batteries. And still, this is tricky with the lithium-sulfur system. And often, when we see publications, the loadings are below 1 or 2 milligrams per square centimeters. And the next sheet is now showing the first experiments of our own. And even so, we had also problems to enhance the loading. We are making suspensions-based cathodes. In this case, they are easy to fabricate. They are all done with commercially available raw materials. In this case, we have a 50 weight% sulfur cathode, so there is another 40 weight% fractions of lightweight carbon. It's a standard carbon, not microporous. It's just like a super P. And we have a 10% binder in it. And we cycled it with 1 C rate, and I always used at least 3 cells to reproduce the results. So therefore, you can see the arrow bars, and they are pretty nice for a 1 C rate. So we are kind of experienced in this by now, but I have to assume I do it for years now. And we not only plotted at the left side the specific capacities, we also made those aerial capacities, and there's the huge difference. While we have here kind of same specific capacities, what were nicely increasing with increased loading. We always had the same amount of electrolyte. It was an electrolyte with 0.7 mole per kilogram LiTFSI and 0.5 mole per kilogram LiNO3 in a mixture, which is quite standard, 1:1 by volume from DOL and DME. And we always had the same electrolyte amount, and therefore we, of course, had different electrolyte to sulfur ratios, and we could raise the capacity a bit, but only not up to 2 milligrams per square centimeter anymore, where there's this first drop again. But there's a huge difference in aerial capacity, as we saw, almost 1,000 milliampere hours per gram as a specific capacity. There's always this linear increase in area capacity. And the 2.0 milligram per square centimeter electrode, which was not the best in specific capacity, still shows the best areal capacity. Yeah, but if we now enhance this is only 20 cycles, and if we enhance the cycles a lot, about 1,000 cycles, it looks completely different, and this is not new. We heard already about it. Dr. Hagen yesterday from Fraunhofer ICT told us, for example, and there's publications also from Dorn Auerbach, and this is the cycle life, which changes dramatically. 0.5 can be cycled without any problems for 1,000 cycles and maybe even more, but then it switches, and also the statistic getting more violent when it really stops, and it is really the cycle life is dramatically shortened, and this is not due viscosity. It is, as we already heard, the fresh lithium is like this one, and then we get more and more depletion on the lithium, and of course when you get a higher loading, then more lithium is stripped and plated again, and this is enhancing the chance of a lithium-induced short circuit. And furthermore, the depletion of electrolyte is increasing because more fresh area is created, and more electrolyte has to deplete into SEI layer. And this is not so much about the viscosity, I know, but then we took our values and we made a lot of difference and said just, okay, this is loading and cycle life, but it is not so much our case. Others already told a lot about it. And we said, let's take just the highest achieved areal capacity during the cycling and apply it versus the sulfur loading, and see, again, we see this linear change, and we see it is not anymore linear after a special sulfur loading, and this corresponds, of course, to its electrolyte to sulfur ratio. And below 10, it is getting worse. And we wanted to increase the loading of the cathode, but therefore, I said it is a sulfur, it is a suspension-coated electrode, and we have a high fraction of carbon in it, and therefore in the PVDF DMSO-based system, the viscosity of the suspension is enormous, it increases, and so we could not further increase the solid content. So we had to increase the loading by a thicker wet coating layer, and due to shrinkage, where during drying, the cathodes exhibited dramatic crackings. So we were forced to do something else. We extended the sulfur loading. We made it up to 78%. The results look completely different. We have a much less obtained capacity. We have only half as much sulfur utilization. And this is at the same electrolyte to sulfur ratio. So it's not the viscosity. It is, of course, the matrix that we provided, and it has much less conductive matrix in it. And therefore, we furthermore gave another electrolyte to it. This was not so much a purpose in this time, but we had one without LiNO3, and we received a dramatically more capacity. Even so, the Coulombic efficiency, of course, was worse, but much higher, a tripled capacity in this system. And in this time, we already thought about, wouldn't it be nice to have more viscosity values about what is happening when the polysulfate is soluble in the electrolyte, where's the viscosity going? And then we furthermore thought, yeah, but there's also an influence of the electrolyte salts on viscosity, of course. And this was then the idea that we wanted to establish a route for viscosity measurements. As you may all know, they're all air sensitive, so we needed to establish something in the glove box, and we decided to take this microvisc device. It's from an American company, and it's a very nice small device. It is developed times ago for the measurement on the field for crude oil, so it's very handy, it's very transportable. It's not a big effort to take it into a glove box, it's there viable. And furthermore, through this, to the kind how it's been measured with this small pipette, there is no sample evaporation during measurement, which is very favorable in terms of these high evaporative solvents. And well, the small sample volume is nice, and a very good over this, a high advantage is that they are often very low viscous and below 1 millipascal second, and this is very reproducible measurement in this very low viscous things. Negative to me is that because how the measurement is done, there is a huge problem with particles in the solution. You can easily damage the sensor with this. And furthermore, we realized that the chip itself, it's measured with a microchip, is increasing its temperature during measurement, and therefore definitely a further, the blue box is it, a temperature control is needed. At least under argon, there's a huge increase of the chip temperature, about several degrees C, and so you can't measure in a stable environment, so you need further this temperature control, and this is, yeah, but it is still handy to have. Yeah, the principle, to point out short about the principle, it is the law of Hagen-Poisson, who says the pressure drop in a tube with constant cross-section is proportional to the length of it. And this is valuable for incompressible fluids with Newtonian flow behavior and a laminar flow. And then it is proportional to its dynamic viscosity. In the measurement instrument, it is made with a rectangular glass flow channel, like it's on the left, with silicon pressure sensor arrays, which makes it a microchip. And the geometry itself makes them a laminar flow, through that the width of the channel is much, much smaller than the length, which assures a laminar flow in it. Furthermore, I had to point out in my case, there's been a Newtonian flow behavior liquids. We checked this. But if it's not Newtonian, it's even so possible. You just need to enhance the equations. Exact, and this is now the first result of what we made viscosity measurements, and this is, as you see, it is really low. Of course, DL, DMA, they all both have a low viscosity, and of course, the one-to-one mixture also had about 0.5 millipascal seconds. Then we added the same electrolytes as we have cycled in, with 0.75 mole per kilogram LETFSI and an addition of further 0.5 mole per kilogram LeNO3. Yeah, we've seen an enhance in viscosity, but the overall viscosity is not as high. TGDME, tetraglyme itself, is much higher in viscosity, but we see similar effects when we use TGDME with high loadings. Yeah, it is, and what made me a little bit curious, and in fact, if you scale down the molality of LeNO3, you receive slower, you receive dramatically lower values of viscosity, sorry. Yeah, and I think this is because 0.5 mole per kilogram LeNO3 in DOL DME are already in part of the solubility border. And therefore, I saw it also today and yesterday, many people still use 0.5 mole per kilogram, or what's very similar molarity. And therefore, maybe it should be reduced and a little bit optimized, because less is effective too. And this is now already my last slide of it. We checked out the green electrolyte without LeNO3, and the blue one is with LeNO3 and LETFSI. And we further thought about what molalities of polysulfides do we need to correspond to the used sulfur loadings that we had. And of course, there has to be much more effort to be taken now. We also should look at the ionic conductivities, and we should further model it then, but we've seen this relation that when we use the next lower loading level, we come without LeNO3 to a similar value than before with LeNO3, and we may see there is something to think about even in these high C rates that we use with 1C, which are already kind of high, and maybe slow down the kinetics therefore. Yeah. Thank you very much. I'm very... Thank you for your time, and I'm very open to any questions if you have.
Hi. Have you looked at the effect of temperature at all?
No, this is all made at 25 degrees C, yes. But this is very likely to do now. And of course, with these high C rates, this is possible that there is a increase of temperature, but this is more or less good for the viscosity because it will sink. Yeah.
Sorry, very nice talk. This is more of a technical question. So you mentioned that for doing reliable measurements of those of the viscosity, you had to implement a temperature control chamber around the viscosimeter. So can you explain how you do that a little bit more detail?
Okay. This is, in fact, it is provided by this American company, which is actually very nice and supportive. And it is just around. It's not easy to use any kind of, especially not water cooling or something like this. So this is a totally air coolant, which really enhances the time for measurements that you need. But it is pre-cooled a half an hour by air cooling or the whole thing, and then you implement the solutions. And then you have to further wait for 5 minutes, and the temperature is always checked directly next to the measurement itself inside the chip. And then, it's air cooling. Is it? Okay.
I had maybe one question. You mentioned you measured your viscosity inside your glove box in argon atmosphere. How did the viscosities changed in a normal atmosphere with oxygen? Whether like an increase or decrease in viscosity?
Well, it's not so much you mean from a pure solvent that there could be an influence?
Yeah, from the pure solvent or solvent with salt.
Okay.
Yeah.
I never put out the solvent with salt solutions. I thought this is not so good for it. We once tried it with polysulfides and got immediately within this pipette, we saw the reaction of H2O. So H2S was evaporating, of course, and this is totally, it is crushing this measurement when there is gas bubble exhausting, because then the measurement itself wouldn't work anymore. But I didn't know that. Do you see any influence by argon or atmosphere for a normal solvent?
I mean, with polysulfides, definitely, because of this reaction, but salt and solvent could maybe be possible.
Because of what?
Like only LaTeFSA salt and solvent, for example, shouldn't react too
We haven't checked it out. This is a very interesting news. I'm from the cathode side more, and the electrolytes are new to me. Maybe we can talk later about this. It's nice to hear about it.
Okay.